Section 7.7. It's called approximation or approximate integrals. So what happened, the idea behind this is we learned how to integrate all different kinds of integrals, including using the U-sub method, integration by parts. We learned how to do partial fraction decomposition, trig integrals, trig substitution. We learned all of this stuff. And what happened is sometimes they give you an integral that is really complicated to integrate or almost impossible, maybe impossible to integrate with the tools that you have so far. So what mathematicians are interested to know is recall what we learned back in previous calculus classes, that if I'm trying to find the integral of f of x dx from a to b, this represents the area under the graph of f of x, right? Under the graph of x. So what they are interested to know, or they like to see, they don't like to say, I don't know the answer to this thing. So instead of, they can say, I don't have the exact answer, but I can approximate it. I can give you an approximation to that. And then over the years, they came up with a course, they called it numerical analysis. So that one, I took it back in graduate school. So numerical analysis talks about a lot of approximations. We have approximation theory and other things. So it's called numerical analysis. So here, what mathematicians are going to do is, you give them a definite integral, or I give you, and you want to integrate it. You got a point like, oh, even the professor cannot do it. But are there ways to approximate this? Well, yes. So you already know half of it from before. So what we did back in Calculus 1, we learned how to use the Riemann sum. Remember? Riemann sum. To estimate the area below the curve before we give you the integral stuff and, you know. So the reason we taught it that way, because it was more tedious to use Riemann sum to evaluate the area below the given curve, right? Then we give you the integral. But now the question is, what happens if the integral is impossible to be integrated? I can't use all the tools we learned. So for example, let's say a common example is the e to the x squared integral from any number to a number, say like 0 to 1 or 0 to 2 or 1 to 3. This one, no matter how you try with all the tools you know, you can integrate this. But I like to see if there's an approximated answer to this by hand, right? I'm going to do it by hand, not using a software or anything like that. So what would be the approximated value for this? So for now, we can use any Riemann sum, the left-hand sum or right-hand sum, to find the this estimated area, right? Now, how did we work with Riemann sum? Well, they tell you, like say, I'm working on the interval a to b. We divide the interval a to b into n sub-intervals. Right, we use that, each with width, we call it delta x, which is b minus a over n. Then that integral that I started with, a to b f of x dx, can be approximated now with the sum of all the areas of these rectangles you're going to come up with, the n of them, n rectangles. So how do I find it? Remember, it was f of x, or here, I don't know what x is, so I'm going to call it xi. Let's call this star like that, delta x, where I moves or changes from 1 to n. See, this is only approximation. Why? You might say, wait, but I've seen that before. Yeah, you've seen that before, but you saw it with a limit. When you do limit as n goes to infinity, that will give you the exact answer. But here it's not exact, it's estimated. It's an estimation. So what is xi star? This xi star, this value falls in, belongs to, or falls in. That's what this sign means. X sub I minus 1 comma x sub I. Now this part there, it could could equal to the sum of xi minus 1 delta x, where I goes from 1 to n, and in this case, this is the Riemann left-ended approach, or left-hand side of the Riemann sum. If we say it's equal to fxi delta x, where I goes from 1 to n, this is the right Riemann sum, R sub n. Another thing we learned in Calculus 1, what Riemann did, not only he did use the left and right, but he also used the midpoint. We call it specifically midpoint rule. The midpoint rule, where after you split it into n rectangles, you take the midpoint of each one of them and that will help you to find the height of each rectangle. So the midpoint rule said you can approximate this integral dx, let's call it mn, m for midpoint, n with n rectangles, which equals to delta x times, when we factor delta x, f of x sub 1 bar, bar means for midpoint, if you remember how we find the mean, plus fx2 bar, plus all the way fx sub n bar. N is the number of rectangles. N is the number of rectangles. Delta x is the width of the rectangle. B minus A over N. N is the number of rectangles. And those x1 bar, x2 bars, just take each interval, take the midpoint, average the two endpoints. And here we have two more ways to approach to estimate the area or the integral. We're going to look at one of them, but not the last one. One is called trapezoidal rule. And the last one is Simpson's rule, but we're not going to cover that out. Just trapezoidal rule. Trapezoidal rule. What is trapezoidal rule? Well, there are two ways I can show you how to get this. One way is basically to get the formula is to average the left endpoint with the right endpoint. So you add them, divide by 2. So to get the trapezoidal rule, we can say the integral from a to b f of x dx is approximated with t sub n, t for trapezoid, t sub n. And what is t sub n here? If I want to prove a formula or get a formula for this, we are averaging. So it's 1/2 the sum of f sub xi minus 1, where I goes from 1 to n, plus the sum of x sub I, where I goes from 1 to n. See, I'm averaging the left endpoint and the right endpoint. So don't forget the delta x in each one of them. And to make it, for simplicity, we can factor delta x out over 2. And now what I'm going to do is I'm going to take I equals 1 in both of them. I equals 1 in both of them. When I take I equals 1, I'll get f of x sub 0 plus f of x sub 1. Plus, take I equals 2. You're going to get f of x sub 1 plus f of x sub 2. Take I3, f of x sub 2 plus f of x sub 3. Plus all the way to the last one, which is f of x. If you take I equals n, you're going to get n minus 1 plus f of x sub n. And what we notice about this, there's only one f of x sub 0. but there's 2 f of x sub I, 2 of them. So 2 f of x sub I, sub 1. There's 2 f of x sub 2, x2, and this can go on and on until f of x sub n minus 1. There will be also 2 copies, and the last one just 1 copy. So this tells me the first one has 1 copy, the f of x sub 0, and the last one has 1 copy, f of x sub n. And that's what it gives me here. So this is the formula for t sub n, where again delta x is the same as before, b minus a over n, and good to know that x sub I is always a plus I delta x. So now, and I can show you graphically why this happens, provided that I'm using the formula for the area of the trapezoid, 1/2 base 1 plus base 2 times the height. I don't know if you like to see it, I can show you. But if not, we can move on to look at an example, how to apply all of this. Now, the example I'm going to choose is not like an impossible example, although I prefer to. But for simplicity, let's take something really simple. Okay, really simple. So how about we're trying to integrate e to the x dx from 0 to 1? Or no, integrate this, call it, let's say 1 to 2. Okay, we need to see what that is. So in other words, you're given a function e to the x over the interval 1 to 2. I know this is very simple, straightforward, which we're going to do that by integrating it right away. The integral of this is just ex from 1 to 2, and that gives me e squared minus 1. If I put that in the calculator gave me 4.67077427. So this is E. Now, how about if I want to approximate? So this is like almost the exact answer. How do I approximate that integral using Riemann sums, right? Right endpoint, left endpoint. Let's do right endpoint. Left will be almost the same. So let's try right endpoint. So here what we're going to do, we're going to choose n to be 5 sub-intervals or 5 rectangles, right? Sub-intervals. Then the first thing I'm going to do is find delta x, because I'm going to use it all the time, b minus a over n. So b here is 2, a is 1, n is 5. So that's 1/5 or 0.2. Right? So I'm going to use the Riemann sum, the right Riemann sum, or the right endpoint. So first one, we're going to use right endpoint to estimate the area below e to the x from 1 to 2. So how do I do this? Watch. So the rectangle started at 1, and then we added 0.2, so 1.2, then 1.4, then 1.6, 1.8, and 2. So 1 to 2. See, 5 rectangles. So when we are doing the right endpoint, we skip the first one on the left. So then we say that integral from 1 to 2 ex dx is about delta x times f of 1.2 plus f of 1.4 all the way to f of 2. See, we're doing the right endpoint, so we skip the first one on the left. So delta x, we found it to be what? 0.2. This one, it's e to the 1.2, e to the 1.4, all the way to e squared. And if you put that on the calculator, that gave me 5.153410575. We are going to use, on the same problem, I'm going to use midpoint rule. So the midpoint, how does the midpoint work? Well, remember, we split that from 1 to 2 into 1.2, then 1.4, 1.6, 1.8, all the way to 2. Right, all the way to 2. Now we're going to pick the midpoints. This is the midpoint, 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 and last midpoint. So the midpoint here is 1.1, 1.3, 1.5, 1.7, 1.9. So these are the values I'm going to use in here. So then I say the integral from 1 to 2 e to the x dx is approximated by m5, the midpoint for 5 subintervals, and this equals to delta x times f of the first one, which is f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. Delta x is 0.2. Remember, the function f is the same as e to the 1.1, 1.3, all the way to e to the 1.9. And when we put that on the calculator, that gives us about 4.66299, 8719. That's what we got. We're also going to do it using the trapezoidal rule. Okay, we're going to move on to the trapezoidal rule. So we're going to apply the trapezoidal rule here. So the trapezoidal rule said 1 to 2 e to the x dx is about delta x over 2 that we proved today, f of x1 plus 2 f of x2. I'm just writing the rule down. 2 of f x3 all the way to f of x sub n. That's what we did. So here delta x, we found it to be 0.2 over 2. F of the first value was 1 on the number line, was 1. Here was 1.2, the next value 1.4, all the way to the last one, f of 2. Then this is 0.1. F of 1 is e to the first, 2e to the 1.2, 2e to the 1.4, all the way to e squared. And when I put that in the calculator, that gives me about 4.686333148. Okay, let's move on with this. So now, what are we interested to know here? So again, the idea is to be able to estimate the integral or the area below the curve, rather than say, we don't know what it is. Yes, we don't know the exact answer, but we can estimate it using either right Riemann sum or right endpoint, left endpoint, midpoint, or trapezoidal rule. Now, what happened is, the first thing I did with this example, I found the actual value, or we call it the exact value. So if you look back at the exact value, it was, so the actual value was 4.67077427. That's the one we found before. This was the exact value, or the actual value. So what happened is, when we find an estimation or approximation, this means that creates something that you always learn in physics and chemistry called an error. There's an error, right? All the experiments is also, there's nothing 100%. So that creates an error here. So the error always, so this tells me when I'm doing f of x dx, the integral, I said, hey, I did the approximation, right? We do approximation. But if I want to make it equal to, I want to switch this approximation to equal to, I have to add the error. So if you take the error, plus the approximation, that will give you the exact, right? The exact value of that integral. So how do I find the error in this case? Well, if you subtract the approximation, so if you take a to b f of x dx minus the approximation or approximated value that you found, that will give me the error. And since I want the error to be positive all the time, I'm going to take an absolute value for that. So in this case, I can say the error is going to be always the absolute value of the actual value minus the estimated. So now I'm going to apply it to everything we found in this example. So the first one we found was to find the error for Rn, the Riemann sum. So it's going to be, the actual was again 4.67077,427 minus, when I found the Rn or R5, it was 5.153410575. That's what we found today. And then when I calculated this, it gave me 0.482636,305. And we did the same thing for Mn, or if you like to, I can do R5, M5. The actual value, the same thing as before, 77427. The midpoint, it gave me 4.662998719, and that gave me 0.007775551. For the last one, the trapezoidal one, T sub 5, 4.67077,427 minus, for the trapezoidal was 4.686333,148, and if you subtract this, you get 0.01555888784. Why do we care about this? We care about this because I'm going to look at these answers that we got. The 0.48 something, 0.00 something, 0.015, da da da. So I'm going to look at the first digit after the decimal point. I see 4, I see 0, and I see 0. So the more zeros you have, the better, right? So the next one I'm going to look at is the last two. Which one is smaller? This has 0, this has 1. So I see the middle one has more zeros, or in other words, the error is the least, right? The error is the least. So that tells me that the midpoint rule gives best approximation. Was this by accident? No. It's always gives the best approximation. Talk about what we call it, the error bound. The error bound. So we put a bound on the error. So it's called error bound. Or error bounds. So we let the absolute value of the second derivative of x less than or equal a number k for x from a to b. Then we have two things. The absolute value of the error in the trapezoidal rule is always going to be less than or equal that k that we're going to find times b minus a to the third power. We're not going to prove this now. Divided by 12n squared. And this is called the error in trapezoidal rule. Error and trapezoidal rule. And the other one, we have the error in the midpoint rule. It's less than or equal to k times b minus a to the third power divided by 24n squared. This is the error in midpoint rule. And I'm going to apply these two error bounds to the example we were working on earlier. So again, in the previous example, we had the function was e to the x. We had a1, b2, and we chose n equals 5. N equals 5. So how do we find the error bound here for the trapezoidal? So k is going to be a value we're going to find here, and the smaller the k, the better. The smaller, the better. So to do this, notice to find the value of k, the value of k deals with the second derivative. Do you see the second derivative? I need to find a bound on the second derivative over that interval from 1 to 2. Right? I'm working 1 to 2. So here, keep in mind that x is going from 1 to 2. That's what a and b are given. So I'm going to find from f of x, ex, we're going to find f prime, which is the same, and we're going to find the second derivative, which is still the same. That's what students like about ex. Right? Now, what we're going to do here is, remember, we need to find the absolute value of the second derivative, means absolute value of e to the x. Now, what do I know about this? This has to be less than or equal to k. So what is k now? Well, if you look at it graphically, this is e to the x. We are working from 1 to 2. 1 to 2. Do you see? 1 to 2. This is 1 to 2. Right? So this here would be e to the first power. This would be e to the second power. Right? So over this interval 1 to 2, what's the highest value the graph could reach? What's the highest value? E squared, right? So this is e squared. That's the highest value, or the maximum value. E squared. Now, what we're going to do is, we found k, we have n, we have a, we have b. We're going to move on and apply the trapezoidal one. So et is less than or equal, again, it's k times b minus a to the third power divided by 12n squared. Right, 12n squared. Let's see, k was e squared, b is 2, a is 1 to the third power. N was 5. And if we calculate all of this, that gives me 0.0246301. If you want to convert that to percent, move the decimal point to the right side 2 steps. That gives me that 2.46301%. I can use the same k value to find e sub m, which is less than or equal k times b minus a to the third power over 24n squared. That gives me e squared times 2 minus 1 to the third over 24 times 5 squared. If we calculate all of this, that gives me about 0.0123150, which is, if you move it to the right side 2 steps, you will get 1.23150%. So if you look at this percent for the trapezoidal and the midpoint, you will find out that the percent for the midpoint is smaller in error, which is expected.